Welcome to the 10th lecture of Optical Sensors course. In the last lecture, we discussed the absorption and dispersion properties of materials, and we arrived to the derived model using Lorentz oscillator, damped oscillator model. We arrived to derived equation for metals, and from there we saw that for noble metals what are the coefficients. We also saw that the real part of the dielectric function of the metals is negative, while the imaginary part is positive. It implied that the metals are absorptive, and because of this positive nature of the imaginary part. In the present lecture, we are going to study what are plasmons, and from plasmons we will arrive to surface plasmons and their dispersion relations. So, from the last turn we saw that when epsilon was defined as is equal to 1 minus omega p square upon omega square, when we did not consider the damping term, gamma was equal to 0. So, when omega becomes omega p, essentially epsilon becomes almost equal to 0. That means, d is equal to epsilon e equal to 0. It means that there are longitudinal waves of large number of electrons. Okay. When omega is greater than omega p, then epsilon omega is equal greater than 0, and the wave is propagating, metal is transparent. If it is less than omega p, then the metal is absorbing and there is evanescent wave. So, minus sign shows that there will not be any propagating wave, and the plus sign shows that there will be a wave which will propagate. Okay. So, this is the physical significance of the last equation which we derived in the last term, and also large reflection, because this is much larger than mod is much larger than 1. So, you saw that it was of the order of 100 or so. So, if you solve for the electromagnetic wave equation, what we see is that for mu is equal to 1, you arrive to this relation, and using this dielectric function you can solve it for this value, which is c square k square is equal to omega square minus omega p square. So, from here you can rearrange it to get omega is equal to square root of this thing. So, omega will have basically two values. Okay. You can put it like this, and what you get is this dispersion curve. So, if you have this red line is called light line, which is when omega is equal to c into k, but for plasmons you have this blue curve which is much large, which is at a larger omega than to the light line. For example, if we have a light which is propagating in light of any wavelength, the frequency omega is of the order of 10 to power 14 radian per second. However, the plasma frequency is this 10 to power 16. So, you can see that it is about 100 orders of magnitude larger. Okay. So, hence the dispersion curve falls above the light line, and EM wave propagation is allowed only for omega greater than omega p. So, if the electromagnetic wave has omega larger than omega p, then the metal is not absorptive. So, what it happens for very high omega values, which is like X rays, maybe X rays also not, then gamma rays and also, so that. So, you have to have very high omega values, that lambda should be very small, so that it does not see the metal. Okay. But for optical frequencies, yes, it is reflective. But what are plasmons? I am all the time asking about speaking about this plasmon thing. What is it? You saw we defined something called plasma frequency. So, let us try to understand what is plasmon. Plasmons are basically quanta of longitudinal oscillations of free electrons in metal. And why it is synonymous, why we call it plasmon? Because it is synonymous to plasma, because there are large number of charges involved. So, you can consider it say for example, you have a piece of metal, you can consider it as a metal of as a sea of free electrons with a positive background. So, you have a solid positive background where you have free electrons moving randomly. The oscillation is called plasmon oscillation. Now, try to understand what is happening there. When a wave travels through a metal, how will it look like? I mean, so to understand this, I have shown this picture. So, suppose I have a pond, and this pond is made of free electrons, and you drop a pebble in a pond. What happens? You see the ripples which are moving away from the point of dropping the pebble, right? What happens inside? As the pebble moves inside the water, on the surface you see ripples, inside the water there will be waves which are cylindrical in nature, and they will be travelling away from this point of origin. So, inside you have waves which are moving away like this, and they are longitudinal because they are moving, they are cylindrical waves which are moving away. On the surface you see this kind of oscillations, which is like kind of transverse wave, but it is not purely transverse, because if you put a small piece of paper on the surface of water, it will start moving this way, right. So, it is not just oscillating this way, but it will also oscillate this way. So, on the surface you have a wave which is partially longitudinal and partially transverse in nature, while in the bulk you have a wave which is purely longitudinal in nature. That is why if you have a bulk piece of metal, the waves in it that are plasmon waves will be longitudinal oscillations, and that is why the electromagnetic waves, most of the electromagnetic waves, they cannot excite plasmons in bulk metal. So, you have to have electron energy loss spectroscopy or something. So, if you want to see excite these plasmons in bulk metal, you have to have high energy electrons, but not the optical photons. But on the surface there happens something that you can excite something called surface plasmons. So, what are surface plasmons? Surface plasmons are coherent collective oscillations of free electrons at the interface of two media of opposite dielectric constant signs. What it means, like metal and dielectric interface. I will come to that when we derive this equation for surface plasmons, but take my word that it has to be an interface of a metal and dielectric. So, what happens actually that this wave, when it travels along the interface, its amplitude decays continuously and it dies out. So, you can see here that we have a wave which is travelling along the interface, and when it travels along the interface, it dies out after certain time distance. So, surface plasmons are the oscillations, and as a result there is a wave which is propagating along the interface, and the field associated to this wave is maximum at the interface and it decays exponentially in both the media. So, this is a wave. If you remember the evanescent wave, if we had evanescent wave, its tail was in only in one medium, right. Evanescent wave was travelling, if you remember, evanescent wave was travelling from n1 to n2 and n1 was greater than n2. So, it was travelling here, but this wave, its field penetrates in both the media, larger in the dielectric, smaller in the metal, that we will come to. Also, this wave is transverse magnetic in nature. So, it is basically p-polarized. So, let us revisit what I taught earlier, that what is the TE and TM polarization for this kind of configuration. So, if you can see this picture where we have an interface of epsilon 1 and epsilon 2, and then an electromagnetic wave is incident at an angle theta 1, which has electric components in the plane of incidence, and magnetic component is perpendicular to this. So, this is p polarization, right. On the contrary, if you have electric field component perpendicular to the screen, then it is p polarized, while the magnetic field components are in the plane of incidence, then it is TE polarized. So, you are clear with this, that in this case the electric field is transverse component, here magnetic field is transverse. So, we are talking about a wave which is basically p polarized. So, I will come to that how, and we will derive it how to solve this. So, for that kind of configuration, the TE mode is given by this set of components, TM mode is given by this set of components, and you can always write the wave equation for TE wave like this and TM wave for this. So, this was in terms of the transverse component, where beta is wave vector of the wave in the medium. In our analysis, it will be wave vector of surface plasmons. So, it will be basically KSP. We will come to that. K0 is the wave vector of light incident which is in the free medium. Okay. So, since it is a surface wave, we solve for the exponentially decaying solutions. So, if you solve for the exponentially decaying solutions of this equation, say for T and T mode equations, you arrive to this relation. Okay. So, you will have two components, and you can see that the plus ones will be exponentially growing, you do not want exponentially growing solutions. So, that is why you have taken only minus ones. So, we have exponentially decaying solutions. Now, we try to solve these equations for the interface. So, let us consider the TMK. So, for z is equal to 0 and z greater than 0, this is the condition, z is smaller than 0, this is the condition. So, we had epsilon 1, epsilon 2. Now, here we have epsilon s and epsilon m. So, if you have an interface which has x here and z here, so here you have epsilon s, here you have epsilon m. This is the metal and this is dielectric. You have metal dielectric interface. You write the E and H components for z is greater than 0 and z is smaller than 0. And now, we apply the boundary conditions at this interface. So, let us apply the boundary conditions for TM waves. So, what are the boundary conditions? This is the boundary condition for TM wave. This is the first boundary condition where the Hy at the boundary should be continuous, and this at the boundary should be continuous. So, we have already talked about the boundary conditions. So, basically you can derive from there, you can arrive to here. What I am seeing here, I mean the other way of looking at the boundary condition is that you do not worry about the electric and magnetic fields, you have a wave say psi is equal to psi naught something sin omega t, you have a wave. So, if it is travelling from here to here, say from 1 to 2, then it has to be constant, continuous. So, psi should be continuous and d psi by d up, if it is z, then dz should be continuous. So, that is what we are doing here. I mean it is not something very, so it is not something you cannot derive from the way the boundary conditions, and what you have here is that for the metal at z equal to 0, it should be equal to the for the Hy for the dielectric at z equal to 0, right. And if you apply that to equation this Hy, you put z equal to 0, this exponential term becomes equal to 0, and what you get is Hy is equal to d, and that is Hy is equal to b. So, basically d becomes equal to b, right. From this boundary condition, what you do is that for the dielectric 1 upon epsilon s dy Hy by dz is equal to this at metal, and put z is equal to 0. So, what you get? Let us write it. So, we had these equations Hy is equal to b e to power minus beta square minus k 0 square, b e to power minus beta square minus k 0 square epsilon s into z, and Hy was equal to d e to power minus beta square minus k 0 square epsilon m z, and we have 1 upon epsilon s dHy by dz. This was z greater than 0, z less than 0, then it will be 1 upon epsilon s into minus beta square minus k 0 square epsilon s z into b is equal to d. So, it will be cancelling out, and that will be equal to 1 by epsilon m minus beta square minus k 0 epsilon m into z. This is what we get. So, here. So, if you simplify it, what you get is that from here you multiply it here and you multiply it here, and then you take common. So, you arrive to this. From there you can have beta square is equal to this divided by this, and you can basically break it in two parts, and you now get beta is equal to. So, something was missing here. So, since this was z then less than equal to 0, so it will become positive here, because z is minus. Okay. So, now that is why you get here plus term in the last one here, minus and then it is plus. Okay. Anyway, so you arrive to surface plasmon wave vector, which is given by this relation. So, now we have a wave which has this propagation constant. So, what happened actually that when we solve for the waves, you can see that it is a wave which is travelling along this interface. So, you can write the E and H components now in terms of the wave vector and apply the Maxwell's equations to arrive to this condition of the wave vector. Okay. So, what it tells? It tells that from here that this are of opposite signs. from here. I was telling that one is going in other direction because of the negative. So, if this has to be satisfied, these are have to be in out of opposite signs, and that can only happen when one material is metal. So, it is not like it is an interface of two media, and if you want to excite surface plasmons on it, then one of it has to have negative dielectric constant, and that is why one of them has to be metal or similar material which has negative value of the real part of dielectric value function. Okay. So, from here we have now real part which is negative. Now, let us see what happens to T modes. So, we see that if we apply these boundary conditions similar to what we did for T m, then for the first boundary conditions we get A is equal to C, and for the second boundary condition we arrive for T actually for T e. We get this, and if you square and sum them, you say that now we know that these have opposite sign. So, this cannot be equal to 0. So, what is equal to 0? This term. So, A will be equal to 0. So, practically there will not be any solution for T wave. So, now mathematically we know that for T m there is a surface wave, for T there is no wave. So, we want to see what happens actually. So, in p-polarized radiation we create actually polarization charges at the interface, and this give rise to surface plasmon modes. So, if you again go to the boundary condition for T or T m, for the T m mode, you know that the electric field is in this plane. So, basically if you apply the boundary condition for D, you have this P1 z and P2 z. Yeah. What are these P1 and P2? These are polarizations. So, basically if you have electric field in the plane of variation of the refractive index, at the interface you are creating polarization charges, and if one of the materials is metal, the electrons will respond to this polarization, and that gives rise to surface plasmon modes. So, that is something very important here. I mean, if you have an interface, I mean that happens, this kind of polarization occurs for any interface, be it a glass and air interface also. You always satisfy this kind of boundary condition at the interface, but if there are electrons which are free, then they respond to this kind of polarization, and because of their response to this kind of polarization, you have this surface plasmon waves. What happens to s-polarized light? Now, incident radiation does not create polarization charges at the interface. Why? You have this plane and the refractive index is varying from here to here in this plane, but the electric field is perpendicular to this interface. So, here what you satisfy for the electric field is the tangential component or transverse component of electric field is conserved or continuous. So, if you compare with the p-polarization where you had these charges, here you do not see any polarization charges. So, if there are no polarization charges, even if you have free electrons, you do not have any surface plasmon modes. Okay. So, that is why surface plasmons are p-polarized in nature, and they can be excited only using p-polarized light. So, in the present lecture we discussed the basics of plasmonics. We also discussed what are bulk plasmons and what are surface plasmons, and from there and then we used the decaying wave solutions to applied the boundary conditions to arrive the dispersion relation of surface plasmons, and from there we also saw that if you want to have surface plasmons, the one of the materials should have negative value of the dielectric function, and that is why we need metals there. Now, if from there we also concluded that we need to have only p polarized light and not s polarized light for the excitation of surface plasmons. In the next talk we will try to see when this wave travels, as I told that when it travels it dies out. So, what is this distance until when it will die out, that we call propagation length. We also said that the electric field will be in both the media and it will be decaying exponentially. So, if want to see what is the extent of this electric field. So, what is the extent of this electric field when it in the metal and in the dielectric. So, if you have the electric field here and you want to see the distance from the interface, this is the distance from the interface. So, you want to see how it changes. Also there are certain issues, I mean with the excitation of surface plasmons. So, if we have a metal and dielectric interface, say this is dielectric and metal, and we want to excite surface plasmons here, there should be something with the wave vector thing. So, we will come to that, but there is something very interesting here, that till now we have studied that this kind of interface supports this kind of modes, surface plasmon modes. In the next talk we will see how to excite these modes. Okay. Thank you.